So in this lesson or review lesson, we're going to talk about some essential graphs. Now, the reason we call these essential graphs is because they're kind of the most basic function related to something you've learned before. So this is a linear function, and you've basically focused on linear functions in grade 10. So you kind of should know what that looks like. And even if you do know what it looks like, I'd still like you to do the table of values. This is the basic quadratic function. You basically focus your energy in grade 11 with the quadratic functions. This one is a cubic function. You may or may not have seen that, but we're going to talk about these ones in 30-1. But that's sort of the most basic cubic you could get. Okay. This one is called an absolute value function. And again, you focused your efforts in 20-1 on this function. This one is the radical function. Now you dealt with radicals in grade 11, but this one is going to come up in grade 12 specifically, where you learn how to graph it, but you kind of learn about radicals in grade 11. This one is called a reciprocal function. And again, we focus our efforts on reciprocal functions in Math 20-1, and we're going to build on these functions in Math 30-1, so you're going to see those again. And then what we do is throw a few more weird functions at you, so I'm just going to call this one a weird one. And the reason that I throw these weird ones at you is just to make sure you're able to take a table of values and try to sketch something you haven't seen before. Another reason that these are weird is because the y is not all by itself, and although these functions are sort of beyond the scope of Math 30-1 or grade 11 or grade 10 math, basically the reason I put them in there is that you don't know what they look like, and I want you to try to predict what they look like using the idea of table of values, which is something you do know how to do. Now, this is a function, again, you may or may not know what this function looks like. This one is called an exponential function, and again, we're going to be dealing with these ones in Math 30-1, but again, it's the idea of a table of values, and you've worked with these types of relationships before, and now it's just taking your knowledge of a table of values, putting it together, and then trying to come up with a graph and characteristics. So what I'm going to do for you guys is go through one example in kind of a little bit of detail, and then let you have the time to work on all the other examples in here. I want you to be both good at using your calculator to look at this stuff, adjusting your window, all that kind of stuff on the calculator, but I also want you to have a good knowledge of how to do these by hand. So any one of the first 6 functions you see, I should be able to tell you linear, and you should automatically be able to take your finger and draw what the basic linear function looks like. I tell you a quadratic, you need to basically take your finger, draw what a quadratic looks like, and sort of know the key features. And that's why we call these the essential functions, because these are sort of the basis functions that we start with, kind of just to help you kind of grapple with graphs and domain and range and characteristics. So the one that I'm going to work on with you guys is the radical function. Only because many of you probably already know what a linear and a quadratic look like. A cubic function you can kind of look at just by using a table of values. Now, when you're choosing your table of values, you want to try to choose all the values that could be possible for that function. So you want kind of a range of values, and I'm going to just kind of write a range of values here. So don't just choose values of one type. Choose many different types. So when we look at the x-axis here, my x values could be negative, my x value could be 0, and my x values can be positive. So I'm going to just start my table at, let's say, -2, -1. And let's just start there for a moment. That will give me a few ideas of what's happening sort of in that negative end. So when x is -2, that's telling me everywhere I see an x, I'm going to be subbing in a -2. So this is going to be y equals square root of -2. And when you try to work that out, it's going to give you a value that's not possible. It doesn't give you a value, it gives you an error. And that's because you can't take the square root of a negative number. So if I do y equals square root of -1, again, not possible. So it's good that I didn't choose very many negative values, but you want to consider them to see, are they possible? The next value I could choose is 0. Y equals the square root of 0. So on my calculator, or just knowing, square root of 0 is 0. So that forms the first point on my graph, which is at the origin, 0, 0. Okay. Now I want to choose some positive values, but it doesn't matter what coordinates I choose for my positive values. So let's say I choose x is 1. Y equals the square root of 1, which is 1. So there's another point on my graph. When x is 1, y is 1. Now, the other thing I want to show you in your table of values is you don't need to move systematically. Let's say I want to jump to 3. Y equals square root of 3. Well, it's not an exact value. If I turn it into a decimal, I believe it gives me 1.73-ish. So I can plot that point. I just have to estimate. When x is 3, y is 1.73-ish. Let's estimate it to be right there. Choose any other value I want. I'm going to purposely choose 9 because I know that 9 is a nice value. 1, 2, 3, 4, 5, 6, 7. Now, although my graph, maybe I won't choose 9 because my graph doesn't actually go to x equals 9. Let's maybe choose like 4 because I know that the square root of 4 is equal to 2 and I can plot that point. So when you're representing your table of values, you just want to try to choose a varied amount of values. We want to label our graph. So I label my graph with the function that is given to me, the one I just graphed. Now, it's also important to label your scale because I don't know what I'm moving up by. So 1, 2, 3, 4, 5. I'm going to label this as 5, and then anybody who reads my graph knows and can figure out that my scale is going up by 1s. Same thing here, 1, 2, 3, 4, 5. I'm just going to make sure my scale is labeled so that a marker would know what my scale is. Now let's talk about key characteristics. So domain, range, x-intercepts, y-intercepts. Let's start with x-intercepts. The x-intercept is an ordered pair of where the graph crosses on this line. Okay, so x-intercepts is where does the graph cross on that line. It crosses right there, and that ordered pair has a location of 0, 0. My y-intercept is a characteristic you need to be able to find. It's asking you where does the graph cross on the y-axis. And so again, it's going to cross at the exact same point, which is located at 0, 0. I like you to write your x-intercept and y-intercepts as ordered pairs. These are called ordered pairs, just because it gives you an exact location of where that starting point is. Now, when I do my domain of a function, domain is a concept that seems to bother people sometimes. What I do is I take an imaginary vertical line of infinite length and I scan my function left to right. So I scan. When my vertical line is over here, my graph, which is the green stuff, does not touch this black line. So this side of my graph, this left side, doesn't exist for my graph. So I want to say, okay, I see no graph, no graph, no graph, no graph. The first point I see graph occurs when x is equal to 0, and then I continue to see graph everywhere where x is bigger than 0. Okay, so I'm going to just kind of remind you about a vertical line just by doing that. We're going to write the domain is the set of all x such that, so this is set of x such that x has to be bigger than, we're allowed to equal 0, or anything else can be a real number. Okay, so we're saying that the domain is the set of all x such that x has to be bigger than 0. Okay, so when I move that, when I take my imaginary line and move it through the function, I'm allowed to be at 0, everything bigger than 0. So basically, I would write that as x bigger than or equal to 0, and then other than that, x can be any real number. You do have to learn this fancy notation for writing the domain and range. Now, when I do the range, I take an imaginary horizontal line of infinite length, and instead of scanning left to right, I'm going to scan bottom to top. So I see no function, no function. The point where I start to see function is at y equals 0, and I continue to see it y bigger than 0. Now, if I'm way up here, all I need to know is my green graph going to touch this line at some point? It will. This green graph will keep going, and the black line is infinitely long. It's going to touch, maybe not right away, but it's going to touch at some point. So we're going to say my range is the set of y such that y has to be bigger than or equal to 0. And while it's bigger than or equal to 0, it can be any real number. Okay? Now, my graph, when we talk about a radical graph, we don't talk about 0, 0 being a maximum or a minimum. This graph has no maxes and mins, although 0, 0 is the lowest that the point or the graph ever goes kind of in relation to x or y, but we say that this graph has no maxes and mins. And equations of any asymptotes, there's no imaginary lines that the functions are starting to approach. So these are my main characteristics for this function. So you're going to state all the characteristics. So again, what I'd like you to do is you're going to go through the linear graph, set up a table of values, make sure you take a variety of numbers that can be possible for x's in each scenario. When you compute out the y, make sure you sub it in to the function. So for example here, if my x is a -2, when I'm computing y, I'm going to be subbing in -2 everywhere I see an x. Watch the bracketing, -2 squared is 4, and so forth, okay? Again, if I sub in a -2 here, remember that I'm going to do -2 cubed, which is -2 times -2 times -2, which is -8, and then go from there. So my first suggestion to you would be to go through the examples without really picking up your calculator. But if you feel like you're not able to do it without your calculator, feel free to use your calculator because you'll be given it as a resource in the course. But basically, you want to be able to try to think through this by hand without a calculator, although sometimes you will be given a calculator. So please work through all of those examples, all 9 of them. And the solutions will be posted on D2L, and you can check your answers and again ask questions as you see they come up.